All right, so we are actually starting a new unit, and that is Unit 2, Applications of Mechanics. And it begins the talking about like applying the unit that we had talked about earlier. And everything that we have talked about will still need to be remembered, such as velocity, acceleration, displacement, and things such as that. Everything that we were talking about there had objects moving in a horizontal direction, which now we are going to start applying that to other directions. So the first part here of Unit 2 is part G, and that's because we utilize the letter G for gravity. And gravity, it just keeps us grounded. It keeps us on our feet, and is a very important part of our calculations moving forward. It is something that is always constantly there. That's why it's a constant. So, near the surface of the Earth, an object is going to experience these accelerations due to gravity. We feel this because we are also near the surface of the Earth. In the absence of air resistance, everything's going to fall at with the same acceleration. We would follow that same way. And then this is a big part of this is in the absence of air resistance. And this becomes a big thing because we can change air resistance. We can change how that is affecting us. And so we need to be very careful about how that works. Some of our calculations are going to say neglect air resistance. That's because air resistance, even though we know that it's a thing, and we know that it's going to change how an object moves, we have to neglect it, say don't worry about it, because it's going to make the calculations very complicated. And we want to keep things some simple ways. Now, there are times in which we want to make sure that we increase our air resistance as much as we possibly can. Say, jumping out of a perfectly good plane. At some point in time, you are going to want to increase your air resistance as an exponential amount. And so therefore, you pull the cord for your parachute and the parachute opens up. And now all of a sudden you go from falling where air resistance is affecting you a little bit, but not a lot. And then all of a sudden it boom, pops open and it opens up. And now all of a sudden you've increased your surface area, and therefore you are greatly increasing the amount of air resistance that you have. And that's important is because we need to be able to do that on certain occasions. Now, air resistance as a car's driving across the road, that's not going to be good because that's why some cars are more aerodynamic, but some cars aren't. And sometimes that's just how that works. And that's going to allow them to move across the road at a better rate. And so air resistance is something that we do know it's happening, it's there, but sometimes for the sake of calculations, we're just going to ignore it. And it's kind of what we would like to do. Now, if there is no air resistance, that means everything moving or falling is going to fall at the rate of gravity. We can think of it as falling in a vacuum. That doesn't mean like the ones that we vacuum up, like on the floor, but it is a vacuum, meaning the absence of air. And if there is no air, there is no air resistance. And therefore, you are allowed to have what's called free fall. And meaning everything is allowed to fall without air resistance affecting it. As the little mouse says over here, you can pretty much fall in free fall until the parachute is opened. The air resistance is there, but it's fairly negligible because of the size of your body is not very large enough, and that's why a parachute when it opens up, it exponentially increases the surface area from you very quickly, and that's why you almost look like they jump backwards, but in all reality is they just decelerated or accelerated in a different direction than what the camera sees, and so that's why it looks like it almost goes backwards, but it's not actually going backwards. So when we look at some of these things falling, we will have to pay attention to some of these terms, and that is, is it in free fall, which is fairly normal? Is the object, what is the time or the elapsed time or the time interval? And so we need to make sure that we all are talking about the time interval for that. And so that is a time interval. With that, and so that time interval is there. So acceleration due to gravity is something that we're going to talk about a lot in this unit. As we can see, the big arrow here is pointing down, and that's because velocity or acceleration due to gravity is always going to be in the y direction. If you remember back, a graph such as this would have a x direction and a y direction, and if you're forgetting which one is which, you can always draw a y on the y axis. This will increase our number of things as well, in that we will have distance in the x direction and distance or displacement in the y direction. Or also means at some point we will have a velocity in the x direction and a velocity in the y direction. For this unit, though, we are going to focus on only, for at least this part of the unit, just the distance and velocity in the y direction, along with more specifically the gravity. We will look at this from unit 1 that we would see here, is that would just be unit 1, that we've already done a lot of that. This will be more of unit 2 and beyond. And so after we get into that, everything can move in more than one direction. Ideally, the value that many times we will use in some calculations will be 9.8 meters per second squared downward. That has a symbol of a lowercase g. For this class, g is going to equal 10 meters per second squared, or 10 meters per second, as would be the easier way to kind of deal with some of the math that we end up doing. Now, an object is dropped from rest. An object will be traveling at these intervals here. Now, where did they get those? Well, they got it from utilizing the acceleration equation. The acceleration equation is equal, if we remember, is v sub f minus v sub I divided by t. Well, if we have it at rest, and that means the initial velocity is 0, and that we are going to then look for the final velocity, the time interval is 1 second, and that our acceleration, because acceleration is also due to gravity, we can say that 10 meters per second squared is that. Now, I would need to solve for v sub f. Well, that means I need to multiply both sides by 1 so that I would have 10 meters per second. That would be equal to the v sub f minus 0, which then gives us the answer of 10 meters per second. Or if we use the more accurate value of 9.8 meters per second. But 10 meters per second will work just fine. Now, what do we do when we get something that's a little bit different? And say that the initial velocity isn't 0 anymore, and that it was 1 second farther down. Well, that would give us this equation. Again, multiplying both sides by 1 will give us 10 meters per second is equal to v sub f minus 10 meters per second. Now, to get v sub f by itself, I need to add 10 meters per second to both sides to give me 20 meters per second, which would be the time or the velocity when time is equal to 2 seconds, because it is 1 second different than the previous time. Now, the same thing would happen as we go down and farther down. So 1 should be able to say, what would the velocity be at 5 seconds? Because at 5 seconds, you would be able to kind of guess that, well, it seems to be that it's the acceleration times time gives me the velocity. And you'd be correct. Now, what's one of the nice things about this is that if we can see in this picture here, there is going to be a point in time that the ball will almost stop into the air. That means its instantaneous velocity is 0, and then starts falling back down as it goes. Now, as the object starts falling down, we would expect it to speed up. At some point, way farther down, the velocity will no longer actually increase. And that's what's called a terminal velocity, meaning the velocity will no longer increase. Now, when that type of thing happens, that means that it's not the acceleration is becoming constant. It has reached that point that the acceleration is constantly being added to it at a same rate. So this usually doesn't happen until extremely much longer or larger distances for an object to fall. So a coin and a feather will fall at the same rate in a vacuum. But usually in the classroom or in normal points in time, we would never see a coin and a feather falling at the same rate. They will fall at the same rate in a vacuum. In a vacuum meaning, again, no air resistance. Because our everyday lives have air and therefore air resistance, the coin will quickly fall to the ground, while the feather, having much larger area, will fall much slower. Now, the instantaneous speed of an object falling at a very specific time is the final velocity in the y direction is used by this equation. V sub Fy is equal to gravity times time. We almost kind of, in a way, proved that equation from the previous example of an object falling. What would the velocity be at certain points? We can also find the distance that the object is going to fall based on the time. Now, this one's a little bit trickier in that it's the distance in the y direction is equal to 1/2, and a lot of times we just say gt squared, but it's gravity times time squared. And we can even solve for time in this case, because sometimes we'll give an idea of how far an object has fallen and now need to know actually how much time it was in the air for that to happen. So these two equations are extremely important when dealing with times and distances when we're dealing with gravity. Such as let's try it out. What would the speedometer of a reading of a falling rock be at 4.5 seconds after it drops from rest. Using the equation, we can find some things out. First off, we're going to say that the T1 would be equal to 4.5. We're also going to say that time at 8, or T2, is going to be equal to 8 seconds. Utilizing the velocity in the y direction final is equal to gravity times time, I should be able to solve for these problems. With this, I'll rewrite my equation so we can see how it looks as I enter the items in here as well. And for the first one, the time is going to be 4.5 seconds. Gravity, as it always is going to be 10 meters per second squared. It is gravity times time to give us a velocity of 45 meters per second. Now, for time in the other, for T2, the second time, at 8 seconds, we have to still use gravity, because it doesn't change. At least it doesn't very much on Earth. And so then we use velocity times, gravity is equal to gravity times time, which will give us 80 meters per second. So that is some quick and easy equations that we will use moving forward.